Here we see a gear train where the gears have different sizes. We want to see what effects that might have on the system here. So our front gear A has a radius of 0.1 meters, but gear B has a radius of 0.2 meters, double the size. We also have a bike tire, which has a radius of 0.4 meters. All right. Now we want to ultimately find the mechanical advantage using the idea that the front gear here is the driver and the back gear is the follower. And so this is going to be the input here, and this one will be the output. Now, mechanical advantage formula says you can use the radius of the output over the input. In this case, that would be 0.2 over 0.1. So our mechanical advantage is 2 here. We'll create more torque by going from a small gear to a larger one. And let's figure out what torque is being applied to the back gear from the ground. It says here that when the tire pushes on the ground with 10 newtons, the ground is going to push back on the tire with 10 newtons as well. All right, now how much torque does that create? The torque of the ground on the tire equals the R of the tire times the force of the ground on tire. Okay, so that's going to be 0.4 meters times 10 newtons. It's 4 Newton meters of torque. All right, that torque that is created by this force needs to be canceled by a torque somewhere else. That's going to happen at this tooth. This tooth is going to be pulled forward by the chain. And how much torque is needed? 4 Newton meters of torque. So to find that force applied to the drive chain at the back gear, we want the formula torque of the chain on B to be equal to the R of B times the force of the chain on B. Okay, we already know the required torque is 4 Newton meters, so that the torques cancel. The radius of B is 0.2 meters. So the force of the chain then is going to be 20 newtons. All right, let's label that. Okay, now the chain is going to transfer the force. And so if 20 newtons are felt at the back gear, then 20 newtons will be felt here as well. So what force is being applied to the drive chain at the front gear? 20 newtons. what torque is being applied to that front gear then? So here's where the difference in sizes of the gears is going to come into play. In some past examples that I had done, the back gear was equal in size to the front gear. So whatever torque the back gear had felt, the front gear would feel too. But now, because of the mechanical advantage, the torques are not going to be the same. We can show that quite simply by this calculation of the torque of the chain on gear A will be the radius of gear A times the force of the chain on A. Okay, so radius of front gear, 0.1. Force, 20 newtons. How much torque is it really now? 2 Newton meters. So that's significant. Before, we had 4 Newton meters on this back gear of torque, but now in the front gear, we only got 2 Newton meters. So there's a mechanical advantage there. So what force does the rider have to push on now that the gears are different? Should the person have to push harder than 10 newtons, 10 newtons, or perhaps even less than 10 newtons? Well, I think it's clear here that if we have less torque on the front gear than we have on the back gear, then the person can get away with pushing not as hard as before. So let's find out what that force would be. The torque of the pedal on gear A is going to be the R of the pedal times the force of the pedal. So we need 2 Newton meters of torque. Our radius of the pedal is just like before, 0.4 meters. And we'll solve for that force of the pedal. And it's now 5 newtons. Interesting. So the mechanical advantage here is that the person gets to push with less force. But there's going to be a trade-off with that. So what's the trade-off here? It says if the angular speed of the wheel is 100 RPM, what will be the angular speed of the pedal? So the formula for this is that the power, it's called, at the input has to equal the power at the output. The energy can't be destroyed or created. It can only be conserved. And so one formula that we have for power is force times velocity. So the input force times the velocity at the input has to equal the output force times the output velocity. But a better formula to use here in this situation would be the other version of this, the rotational version, which says that the torque input times the omega at the input has to equal the torque at the output times the omega at the output. Let's see what happens when we plug in our numbers. So our input torque is 2 Newton meters. And we want to find that input omega. That's what we're being asked for. The output torque is 4 Newton meters, and the tire is rolling with 100 RPM. Now, if we solve that equation, 4 times 100 divided by 2, you get this, that omega in, has to equal 200 RPM. So that's the trade-off, is yes, you get to push with less force, but you have to make more revolutions now. And so really no power or energy is gained here. The work that you do ends up being the same. So for 3G, the answer is same power.